Hello and welcome everyone to Iris Biotech's third online workshop 2022. True to our slogan, Empowering Peptide Innovation, we are keen on knowledge exchange and getting in contact with scientists all over the world. Therefore, we started this workshop series last year. Today, our focus is on greener peptide synthesis. Together with our colleagues of Sulfotools, we will give you an introduction to the clean peptide technology, the use of SMOC amino acids to replace organic solvents in peptide synthesis by water. My name is Raimund Meyer. I am working as a project manager at Iris Biotech, and today I will guide you through this online workshop. If you wish to announce your participation on social media, please feel free to use the hashtag Iris Workshop Series, which is also displayed right now in the Microsoft Teams chat. To have a pleasant experience for all participants, I would like to begin with some technical guidelines. To ensure the best possible audio and video quality, all participants are automatically muted and your video camera is switched off. Another important information is that this live event is recorded. Thus, if you enter late or miss anything, please check the bottom left side of your Teams screen if you are watching the recording or if you are live, which is shown by the red broadcasting symbol. You have the possibility to pause the video, rewind or jump back to the live session. In addition, the recording of the workshop will be uploaded on our homepage afterwards. Questions can be submitted by using the Q&A chat of Microsoft Teams. You can enter your name or submit your questions anonymously. We will frequently check the questions, publish them, and submit them to the respective speaker. If you have any technical queries, you can also submit them in this Q&A chat. Our technical assistant will then connect with you and try to solve the problem. Initially, the questions are just visible for the organizers and will then be published to the audience. So don't worry if your submitted question does not appear on the chat screen immediately. To try out the Q&A chat, we will now post a question which you can answer. Now you should see within the chat the question, which solvent becomes applicable in solid phase peptide synthesis through SMOC clean peptide technology? Please feel free to answer it to try out this Q&A chat tool. Okay, so we already see answers are coming in, and of course, the correct answer is water. So as this seems to work, I would like to quickly give you an overview on today's agenda. We will start with a short company and topic introduction by our project manager, Karin Rustler. Afterwards, our external speaker, Christina Uth and Sascha Knauer, will provide detailed information on their research and applications of water-soluble SMOC amino acids. As mentioned, questions will be collected throughout all talks in the Q&A chat and are forwarded to the speakers. Of course, you can also get in contact via email or phone call after this workshop. One last note from my side, if you accidentally close your Microsoft Teams window, don't panic. The workshop is also available as recording. You will not miss anything. Just relog in and view the recording. You can also then play this recording at increased speed until you catch up with the live event again. After this technical intro, let's now continue with the first agenda point, a short introduction to our company by our project manager, Karin Rustler. Karin studied biochemistry at the University of Regensburg and obtained her doctoral degree in organic chemistry for the synthesis and characterization of photoswitchable compounds for biological application. During her PhD, she stayed abroad at Kyoto University, Japan for several months. Beginning of 2020, she joined Iris Biotech as a project manager. Karin, thank you for your precious time. Please go ahead with your presentation.
Also, welcome from my side to today's workshop. I'm sure you are all curious about the main topic today, so the peptide synthesis in aqueous media. So I try to keep my introduction rather short. Iris Biotech has been founded in 2001. We are located in Madridwitz, Germany. Together with our partners and distributors, we are spreaded and represented all over the world. In 2013, due to the growing demand for customized products, we founded the Iris Biotech Laboratories, which are also located in Germany. Beginning of last year, we decided to refresh our corporate design and switch to a more modern logo, which you can see over here. And just for comparison, in the middle of the slide in here, in blue-yellow, you can still see the old one, which we had in the beginning. To give you not only facts and figures, I would like to show you that Iris Biotech is really surrounded by beautiful landscapes and natures. And also the company building, I think, is not too bad as a place to work at. Our mission as qualified supplier and competent consultant is to support our customers in their ongoing projects from research scale to commercial production, from standard consumables to exotic building blocks. Thereby, our portfolio ranges from products for peptide synthesis, modification and purification, over linker technologies for advanced conjugation, towards drug delivery. And, as mentioned in the beginning, for the products which you cannot find in our catalog, we are offering custom synthesis. Besides, we are publishing topic-specific brochures and flyers containing detailed explanations and protocols surrounded by suitable products available at Iris Biotech. All those materials are available as free download on our website. This collection of brochures and flyers already highlights one aspect which is very important to us, namely the exchange of knowledge. Or, if we want to put it in other words, our guiding principle is empowering peptide innovation. This means that we are in frequent exchange with researchers all over the world. We are attending various conferences, and we are looking for innovations and new creative ideas, and this also in terms of sustainability of peptide synthesis. You may ask why, peptide synthesis already exists as it is for several years, but most of you know that following modern regulatory rules, undesired solvents such as DCM and DMF should be replaced, and also the use of DMF will be more and more restricted. Besides, peptide manufacturing in general generates a huge amount of waste. Regarding the topic sustainability, some time ago, we already presented the use of alternative solvents for resin loading, as well as the Peptide Easy Clean technology for peptide purification. If you are interested in those topics, both articles are available on our website. Today, we want to focus on peptide synthesis using water instead of organic solvents. Already some years ago at the German Peptide Symposium, we got aware of sulfatols and their SMOG amino acids. Over all the years, we stayed in contact, and today we are pleased to have Christina and Sasha with us as our external speakers. And with this, I would like to say thank you for your kind attention for my introduction, and I would like to pass on to our main act, sulfatols. Thank you.
Yeah, thank you, Karin, for giving this introduction. As there are no questions to this presentation, let's go on with our highlight. Switch to our external guest speakers, Christina Uth and Sascha Knauer of Sulfotools Germany. Christina Uth studied chemistry at the universities of Darmstadt and Heidelberg, focusing on biochemistry and organic chemistry. During her PhD research, she worked on the development of bioorthogonal synthetic strategies towards hybrid macromolecular conjugates with tailored properties. Sascha Knauer studied chemistry also at the Technical University of Darmstadt. Also with a focus on biochemistry and organic chemistry, and during his PhD, he worked on aqueous solid phase peptide synthesis, a novel concept of peptide synthesis. Both of them hold a doctoral degree in chemical engineering. In 2016, Christina and Sasha together founded the company Solvents to further develop and commercialize their aqueous solution-based clean peptide technology. For their work and with their company, they won several prizes already. For example, they were appointed as winner in the German Brand Award category Chemical Industry, and in 2020, they received the German Innovation Award for Climate and Environment in the category Sustainable Technologies. Christina and Sasha, it's a pleasure to host you as our guest speakers. The stage is yours. We're looking forward to hearing about your research, and for the audience, please post your questions by using the Q&A chat.
Yeah, so thank you very much for the kind introduction and for having us. I would like to also welcome everybody to our webinar. So let me start with why we are all here. It's of course the problems of current peptide production. As you all know, it requires immense amount of organic solvents, which leads to environmental implications. Also, there are regulatory restrictions, as Karin already told you. DMF is classified as substance of very high concern by the REACH regulation, and the EU Commission has decided to restrict its use from December next year. Altogether, this leads to very high production costs. So, for instance, the global annual demand of pharmaceutical peptides, only pharmaceutical peptides included, is about 1.8 tons. To produce 1.8 tons of, for instance, 27 amino acid long peptide, which is the average length of a pharmaceutical peptide, it requires at least 50,000 tons of DMF or other organic solvents. And for the purification, additional 25,000 tons. This is reflected also in the cost split of the raw materials, where solvents alone make over 80% of the costs. All these problems are well known and were summarized in a recently published paper from the ACS Green Chemistry Institute Pharmaceutical Roundtable, where all big pharma companies are members. They also publish the demands they have for a greener peptide synthesis. So to address these problems, several approaches were published and developed. For instance, in 2009, the solid phase peptide approach in water was published using microwave-assisted heating. However, this is of course not scalable and of course too energy consuming. The Hoyo et al. Published an approach with water dispersible FMOG or BOC protected amino acid nanoparticles, also using microwave irradiation. But this has the disadvantage that the washing steps still have to be performed with organic solvents. The same working group also published new water-soluble protecting groups shown here, but they all have intrinsic disadvantages. For instance, restricted stability or moderate water solubility. They are all very expensive and complicated to synthesize, and in case of cysteine and methionine, auto-oxidation was observed. The CEM Corporation claimed in a patent application another water-soluble protecting group, the so-called NSMOG group, but they dropped the patent because the synthesis of this protecting group is very expensive and has a very complicated deprotection mechanism. Another approach was to use novel surfactants as nanoreactors to synthesize dipeptides in water, but of course this is also very limited in scalability. Another approach is a solvent-free peptide synthesis using ball mills, which was published in 2009. But this was also limited to rather short peptides. They synthesized 5 mers. A very recent approach is to use water polar clean mixtures. Polar clean is a polar solvent or co-solvent used in agriculture. They were introduced for the circular aqueous peptide synthesis, which work quite well. There are many other attempts to substitute DMF as solvent with greener organic solvent or solvent alternatives. For instance, there's Cyrene, distributed by Merck, as a bio-based alternative, which is derived from cellulose, or Bachem in collaboration with Novo Nordisk investigated binary mixtures of different polar organic solvents, and they use in peptide synthesis. Or to other publications, we found they used the gamma valerolactone and formyl morpholine and propylene carbonate as solvents for peptide synthesis. However, the conversion is often limited by the application of FMOC amino acid building blocks due to their low solubility. Our approach is based on new water-soluble building blocks, structure you see in the middle, the use of which allows us to substitute organic solvents with water, thereby reducing the amount of hazardous waste. And due to intrinsic fluorescent properties of the molecule, it allows for the first time real-time monitoring of the reaction progress. We have also developed a purification concept and a wastewater treatment option. Altogether, this leads to a reduction of process costs of up to 50%, an efficient use of chemical resources, an eco-friendly, more sustainable process, and of course, solvent-free end products. So let us have a closer look to the SMOC protecting group. It is based on the FMOC structure. Merrifield introduced in the 70s already the monosulfonated variant for peptide purification purposes, and our SMOC is the desubstituted or the desulfonated variant. The molecule has a unique combination of water solubility and intrinsic fluorescent properties. So there are two different methods for the synthesis of SMOC-protected amino acid. The first one is the direct sulfonation of FMOC-protected amino acids, which is in some cases possible. And another variant is to use SMOC chloride and protect the respective amino acid. Here shown is an exemplary HPLC chromatogram of SMOC alanine and the side products which can occur during synthesis. So at 7.8 minutes we have the SMOC alcohol, at 11 minutes we have the SMOC alanine, and there's of course some monosulfonated variants of both. Relevant for peptide synthesis is only the monosulfonated SMOC amino acids, but it reacts equally as the SMOC amino acid, and we did not observe any side reactions with the SMOC alcohol or the monosulfonated alcohol. So then we took a closer look at the SMOC deprotection. We tested different bases in aqueous media, as shown here in the table, and we found that SMOC is more base labeled than FMOC. So we can reduce the amount of base and therefore reduce the base catalyzed site reactions. Here shown is excitation and emission spectra of S-glycine. As we already told you, there are intrinsic fluorescent properties, and as you can see, there's a small Stokes shift, and this would allow for an inline monitoring of the coupling and deprotection step, and an automated decision whether another coupling step is needed. But we did some research with an on-resin monitoring, but of course the solution monitoring would be more preferable. But this needs a bit more work. So now my colleague Sasha will take over and introduce the details of our technology.
So the most important part for peptide synthesis in aqueous systems is, of course, the coupling efficiency of amides in water-based systems. Therefore, we made a series of experiments with a small system with S-proline, tyrosine or methyl ester as a model system with various coupling reactions with sodium hydrogen carbonate as a base, and tried different solvent systems. As you can see here, the most efficient coupling system for in situ coupling is EDC Oxima. Pure coupling efficiency in pure water is around 90.7%, which is better than all other systems in comparison. And interestingly, the coupling efficiency is highly increased by adding up to 30% acetonitrile, ethanol, or isopropanol, resulting in coupling efficiency of 99.8%. So it's quite comparable to standard organic synthesis in DMF. So this is basically our adapted SPPS strategy. Of course, it's based on Merrifield's SPPS strategy. We start with a water-compatible resin. There are some commercially available, like Tentagel or Chematrix resins. There are also some other resins available for polar solvents. So the first amino acid is coupled to the resin, followed by an alpha deprotection, and then the next activated amino acid is added. And we added an optional capping step with either sulfonated acetic acid, for example, or normal acetic acid. It's depending on the purification strategy that is chosen afterwards. If you use the sulfonated label, we have our correct intermediate and sulfo-labeled side products. And if we repeat the cycle n times till our peptide is synthesized and cleaves the peptide from the solid support, we have our target peptide in solution. We have a series of labeled side products in solution, and of course cleaved side chain protecting groups. And if you run this mixture over an ion exchange column, all sulfo-labeled impurities stay on the column, and only the target peptide is able to run through. Of course, it can be done the other way around with conventional capping with acetic acid and putting the last S-MOG protecting group on the resin, and so the peptide will stay on the column. This is the way that Merrifield designed its purification method. Here are some examples for peptide synthesis. This is a small peptide that's interesting in the cosmetic industry. It is PAL-GQ-PR. This was synthesized on a preloaded HNPB Chematrix resin, and coupling were performed with 2 equivalents of the S-MOG amino acids, 4 equivalents of EDC, 2.2 equivalents of Oxima in 20% ethanol, and as base 3.5 equivalents of sodium hydrogen carbonate. Deprotection was performed in 20% ethanolamine for 5 and for 10 minutes. Coupling of the palmitoic acid was performed in higher molar excess. It's necessary to go up to 90% in ethanol because of the low solubility in aqueous media. The purity shown of the crude peptide is here. It's around 86% and confirmed by MS. So the next example is the synthesis of an S-MOG heptaarginine. This was done on a Chematrix rig amide resin. The resin was loaded with 3 equivalents of the SMOG amino acid, 5.5 equivalents EDC, 3.5 equivalents oxima, and 3 equivalents of sodium hydrogen carbonate. Synthesis was done with double coupling steps, or the resin loading, sorry. Coupling was done with the same conditions, but only with single coupling steps in 30% acetonitrile. Deep protection in this case was performed with 1 molar sodium hydroxide, also for 5 and for 10 minutes. The interesting part is that it's possible to use arginine and water-based synthesis without side chain protecting groups, which is removing some of the problems during the organic synthesis of heptaarginine, where after cleavage from solid support, up to 3 PBF protecting groups are still detectable by ECMS. This is an example. We are not allowed to show the sequence, unfortunately. This was a cooperation with a pharma company. It's an octapeptide they used for fragment condensation. It was also performed on a chematrix ring amide resin. The resin and the coupling were performed under similar conditions with 4 equivalents of the SMOG amino acids, 8 equivalents EDC, 6 equivalents oxima, and 1.3 equivalents of sodium carbonate as a base. Resin loading was done in a double coupling, normal synthesis in single coupling steps, and deprotection was performed with 1 molar sodium hydroxide again. Shown is a crude HPLC of the peptide synthesized in pure water. Here's a comparison of the organic synthesis performed by the pharma company. Crude yield were about 500 milligrams, HPLC purity were 90.7%, and the racemization of the shown amino acids is quite low in organic synthesis. We did the same synthesis in pure water. Crude yield were about 420 milligrams with 78% purity. Racemization was a bit higher, and the same synthesis in water with 20% acetonitrile is resulting in a nearly the same crude yield and an HPLC purity of 82% with the same low racemization level in the organic synthesis. The last sample shown here is the synthesis of vasopressin as a more complex peptide. Synthesis was performed on a ring amide chematrix resin again. All coupling steps were performed as double coupling steps with 3 equivalents amino acid, 5.5 equivalents EDC, 3.5 equivalents oxima, and 3 equivalents sodium hydrogen carbonate as a base. Again, in 30% acetonitrile. As double coupling steps, deprotection was performed with sodium hydroxide again. As you can see on top, this is a crude peptide after cleavage from solid support. Afterwards, followed by an oxidation of the disulfide bridge in aqueous systems. This took around 3 days. Yeah, could be optimized for the oxidation. So here's our recommended procedures for starters for using SMOG technologies. The method 1 is the in situ oxima coupling, shown as before. For starters, for the beginning, before optimization, we would recommend to start with 3 or 4 equivalents of the SMOG amino acids, 5.5 equivalents EDC, 3.5 equivalents oxima, and 3 equivalents of sodium hydrogen carbonate in either 30% isopropanol or acetonitrile, and 45 minutes of coupling time for single coupling, or 2 times 25 minutes with double coupling steps. Washing steps could be performed with simple water. Deprotection could be performed with 1 molar sodium hydroxide. Important is here, if ester side chains are present in the sequence, it's necessary to use other bases like piperazine, for example, or for methylpiperidine. Otherwise, sodium hydroxide would cleave the ester side chains as well. Washing after deprotection should also be performed with water. A general recommendation is that ring amide resins needs to be totally dry before cleavage from solid support. Otherwise, there are side reactions that occur. As I said before, recommended resins are Tentagel chematrix. These are the resins that we use normally. Of course, there are quite a series of other resins available that could be used for polar solvents, but we didn't test all of them, of course. The method 2 we would recommend is NHS ester formation as a pre-activation. This could also be performed with 3 equivalents of the SMOG amino acids, again 5.5 equivalents EDC. In this case, 3.5 equivalents NHS in water. If all of these compounds are diluted in water, the pH should be in the range of 5 to 6, 25 minutes pre-activation time. This could also be monitored by HPLC to see the amount of pre-activation as NHS ester. The coupling is then performed by adding the whole mixture to the amine and adjusting the pH to 8 and readjust over time. If the pH is constant and is not dropping for over 2 minutes, and the reaction is finished. Washing again with water, deprotection as before. Sodium hydroxide is the easiest one. If ester side chains are present, use an alternative. And washing steps again only with water after deprotection. So the most interesting part, of course, is racemization studies. Most of the people think peptide synthesis in water should result in high racemization levels. We made 2 peptide sequences shown on the top. These were sent to cut tubing for analysis of the racemization levels. As you can see, there's no increased racemization levels detectable in a water-based synthesis. Interestingly, the racemization of cysteine is quite low. It's even lower than in most organic synthesis. The racemization of asparagine or aspartic acid is a bit increased. This could be related to an aspartimide-based racemization process in the synthesis. And of course, this leads us to the more serious side reaction in peptide synthesis, aspartimide formation. As most of you should know, it's based, of course, on asparagine or mainly on aspartic acid in a base catalyzed side reaction, resulting in the cleavage of the side chain protecting groups. This is resulting in a cyclic intermediate, the DL aspartimide formation. And there are 2 possible reaction ways afterwards: a simple hydrolysis, which would result in an alpha peptide or in a beta peptide. Racemization is also possible for both structures. And if organic bases like piperidine, for example, are used, it's also possible that the 2 base educts of the alpha and the beta product could occur. To check this aspartimide formation in water, we synthesize the peptide scorpion toxin 3. The sequence is shown here. It's a sequence that is well known to be prone to aspartimide formation due to the motif DG, which is one of the most problematic motifs, of course. We split the synthesized peptides in multiple fractions and incubated them for 3 and for 16 hours in different bases. Shown here is the HPLC of our target peptide. We also synthesized some of the potential side products, the D peptide or the beta peptide as potential side products. As you can see, if we incubate for 3 hours in 1 molar sodium hydroxide, there's clearly a shift to the beta product, and but the target product is still visible. If we use, for example, a weaker base in water, like 5% piperazine in water, there's a minor shift to the beta peptide. In DMF, after 3 hours, there's no observable side reaction. Piperidine, it starts to produce side products, and yeah. After 16 hours, the strong bases, of course, look pretty the same. Interestingly, is piperazine in water, so the level of aspartimide formation increases. It's a higher amount of the beta peptide visible, and with piperidine, interestingly, it's more or less only the base adduct visible, whereas in organic synthesis, the only visible side product is the beta peptide, so it's a complete different mechanism. Interestingly, the observed levels of, let's say, nearly by piperazine of 1 to 3 or 3 to 1 to the target product here are correlated to formations of aspartimide formation in proteins, which is also called aging of proteins. For example, was observed in literature in the same amount in the amyloid beta proteins, for example. So of course, aspartame formation is temperature dependent. To prove this, we made the same experiment again, only with 5% piperacin in water. We incubated for 3 hours with 3 temperatures at 4 degrees Celsius, at 26 degrees Celsius, and 40 degrees Celsius. And as you can see, of course, the change is clearly visible from the beginning of product ratio of alpha to beta product is 3 to 1. And if you incubate at higher temperatures, the ratio is switched to 1 to 2.5 to the beta product. So aspartame-bound sequences should be synthesized at low temperatures, but this is also true for organic synthesis to reduce the amount of aspartame formation. And of course, use the weakest possible base. So the last aspect of peptide synthesis, of course, one of the bottlenecks is product purification in the end. There are 3 key drivers for the optimal purification process: productivity, yield, and solvent consumption. And these 3 are linked together, of course. As you can hear in this short graphic, of course, if I want to increase the target yield of the peptide, solvent consumption will go up, resulting in productivity going down. Of course, so for many peptides, the target yield of 50% is accepted in terms of solvent consumption in an acceptable amount, but is of course depending on the price of the peptide. Just a short reminder of our purification concept. If we use our capping strategy, or the other way around, we have a target product, a side product, and a click protecting group. And if we put this on an ion exchange column, either the target peptide runs through and the impurities stay on the column, or the other way around. And this part of purification could be used as either a pre-purification or as part of the multi-column systems to reduce the amount of organic solvents necessary for the HPLC purification. Here, 2 model experiments to show that this concept works quite well. We did a model experiment. We synthesized hexapeptide 9 in water and did a capping strategy with 2-sulfoacetic acid, shown here. And we coupled all amino acids with 0.95 equivalents compared to Breyer coupling in order to achieve a maximum amount of byproducts. After cleavage from solid support, the crude peptide is shown here. This would be the target peptide. If we run this on an ion exchange column with a pH range of 1 to 3, the target peptide runs through, and nearly all impurities are removed. TFA is still some left in the mixture. The same method also would work in a DMF-based synthesis, of course. We did this in the synthesis with adrenorphine. We did the same experiment, and this time we used 4-sulfobenzoic acid as capping reagent. Did the same experiment, have a series of side products. After ion exchange, only the target peptide runs through, and most of the impurities stay on the column. As I mentioned before, of course, we can use it the other way around, like Merrifield designed it in the 70s. We do a normal capping strategy with acetic acid or acetic anhydride, similar to the FMOC chemistry capping. The last final SMOC protecting group remains on the peptide sequence. And after cleavage from solid support, the whole mixture is put on an ion exchange column, binds there to the column. And after washing steps, this is a crude example we synthesized. And it's possible to either elute this SMOC protected peptide from the column, depending on the ion exchange material you need under these conditions, or it's possible to do an SMOC deprotection on the column directly and elute only the deprotected target peptide afterwards. So wastewater treatment is of course done in the same way. EDC is a polar coupling reagent. The SMOC protected amino acids are also highly polar and have all ionic groups. So we can remove nearly all impurities in the wastewater via ion exchange columns. Here's an example of the best visible impurity. If you run this on an ion exchange column, only purified water runs through. This is also visible by fluorescence measurements, and afterwards it's possible to either regain the amino acids or to put them to waste and reduce the amount of waste, of course. Yeah, then thanks for your attention, and we are looking forward to your questions.
Yeah, thank you very much, Christina and Sasha, for sharing your results with us. During your presentation, we have indeed collected quite some questions. The first one came quite at the beginning. You showed the beginnings of strategies for water-soluble peptide chemistry, and microwave-assisted peptide chemistry was often a topic there. So is the SMOG amino acid also used in automated microwave-assisted peptide synthesis as the FMOGs?
So basically, I think it should be possible, of course, to do automated water-based peptide synthesis. If this is possible with microwave irradiation, I'm not sure about it. Increased temperature will result in increased racemization levels. This needs to be tested if this is in an acceptable range for peptide synthesis, or if racemization in water at increased temperature might be a problem.
Okay, because this is also in accordance with a further question. Have you evaluated the effect of higher temperature of amide coupling on ASPPS?
Yeah, basically it's known in the literature, of course, if you increase the temperature, amino acids have a higher tendency for racemization. This is also a problem in organic synthesis. So I would guess that the same experiments would result in higher racemization levels in water as well. But there are no experiments so far that prove this might be in a range that could be a problem for peptide synthesis.
Okay. So then there is one question. I don't know whether you want to answer it at all. The question is there a protocol you would recommend to convert existing FMOG amino acids to SMOG amino acids? I would say they could look up your patent. Don't know whether you want to comment on that. I can comment from our sides that the SMOG standard amino acids, the canonical amino acids, are available from Iris Biotech.
Yes.
I don't know if you want to comment further.
I mean, of course, it would be possible to test if some amino acids would work to sulfonate directly, but I think it's difficult to purify them.
I think so. Then one similar question to that, are the SMOG amino acids themselves also made without organic solvents, or do you need, say, classical solvents for that?
So the SMOG amino acids are protected in aqueous media as well. Normally we add either 20% acetonitrile or 20% isopropanol during the synthesis of the SMOG amino acids, but it's in aqueous media.
Mm-hmm. Then many questions are about the resins you were using. So, for examples, first one was really what kind of resins can be applied for the water-based peptide synthesis, or are the Chematrix resins shown in your examples commercially available from Iris Biotech? And another question, do you have preference for Chematrix resins versus Tentagel? And then one person already pointing that out, if Chematrix, then what next would you recommend given the Chematrix discontinuation? I guess this is a topic that several peptide chemists are not aware of yet. So the owner of the Chematrix technology has decided to discontinue the production of chematrix resins. So we saw that you also did quite some things on Tentagel. What are your recommendations?
So basically, the chematrix resin is completely based on the completely PEG-based resin. The Tentagel has a polystyrol core with PEG units as a linker before the functional groups. Both work quite well in peptide synthesis. Depending on the peptide, sometimes one works better than the other one, but yeah, I think there are also some alternatives to chematrix, of course. There are other resins that are completely PEG-based, for example. But yeah, I think there's no definite way to say this resin is better than the other one.
So my first idea indeed would be, of course, when you do no longer have chematrix, definitely Tentagel is my first choice in this. Anyway, Iris Biotech and also others are currently also working on other, say, higher hydrophilic resins that have good swelling properties in water. I guess there are quite some things to come in the future.
Yeah, definitely.
So further questions are typically about the solubility. So, for example, what about the solubility limits of hydrophobic SMOC amino acids, such as SMOC phenylalanine? Or another question, have you stress tested the level of peptide hydrophobicity that still works fine in water?
So for the first question, the SMOC group is increasing solubility for many hydrophobic amino acids, for example, tyrosine, which is nearly insoluble in water as natural amino acid, is quite good soluble, for example, as SMOC protected amino acid. And for the question of the hydrophobic character of the peptides, this is of course related to the side chain protecting groups. We need less side chain protecting groups for most of the amino acids we use. Glutamine, asparagine, tyrosine could be used in many sequences without side chain protecting groups. Arginine doesn't need a side chain protecting group. So there are also polar aspects, of course. And to be honest, most of the currently used side chain protecting groups like BOC or ETA or ester protecting groups have a quite good water solubility. So we didn't observe any problems, of course. There might be a problem we haven't checked yet. What happens if we put, let's say, 8 tyrosines or 8 other strongly hydrophobic amino acids in a sequence? We tested like 8, let's say, hydrophobic amino acids like leucine, isoleucine in a sequence, and up to 8 amino acids, water solubility was not a problem. Okay,
that sounds good. One quite similar question, what resin loadings have you been able to demonstrate aqueous SPPS with? So I guess that's also in the same direction with solubility.
Yeah, so basically the resin loading is of course strongly depending on the used resin. The chematrix resin and I think the Tentagel are in a similar range of 0.3 to 0.6 millimole per gram. I think at the moment there are no high capacity resins available for aqueous synthesis, but this might be a point to the future for the development.
Okay, so one question about aspartamide formation. Have you already tried the CSY protecting group, the ASP-CSY, in water for avoiding aspartamide formation? That's the protecting group developed by Jeffrey Bodie from Zurich.
So we have that protecting group here, but we haven't had time to test it. But this is still on the agenda.
Okay, so as soon as you have results, please let us know.
Yeah, we will.
Okay, so let me go through. One question, congratulations for this very impressive work. few questions. One of them is about the resins again that you already answered. So what maximum peptide length have you reached with your strategy, and have you ever tried automation on the synthesizer?
So we did some experiments with automatization, but there are only some proof of concept experiments. So basically it should work. It's a bit depending on the synthesizer, if it could simply be switched to water or not. I think the Liberty Blue, for example, is quite difficult to switch to water. There would be a technical support necessary. Other synthesis devices like, it's depending on the device, I think should work quite well. And sorry, what was the first part of the question?
The maximum length of a peptide you made.
So the maximum length of peptides we synthesized in one step was 12 amino acids so far. Longer peptides have been synthesized by fragment condensation, but this was related to the projects that we performed that was planned in the beginning for fragment condensation. So we never tried if it's possible to do it in a single step.
Okay, so several other questions going in the same direction. Have you tried automated synthesis? With which brands of automated machines did you test? You already answered in this direction. One that you already commented on, how do you deal with trifunctional amino acids like lysine and aspartate? Is there any soluble side chain protecting groups? You already commented on that. Indeed, it is not necessary to make them more soluble, right?
Let's say for cysteine, for example, if you use a standard trityl protecting group, it's necessary to increase the amount either of acetonitrile or isopropanol up to 50 or 60% to use the standard side chain protecting groups. But of course, there are other side chain protecting groups available that would have a higher polar character that would allow to be better used in a water-based peptide synthesis, but there's still some room to test.
Then one question to the ion exchange purification. Thank you for your very interesting presentation. For a direct comparison, do you have data related to product yield and purity before ion exchange purification of FMOC peptide synthesis versus SMOC peptide synthesis for identical end products?
No, so that we didn't do. We have shown you the data we have. This would of course be interesting. So, but we focused in the last year to optimize SMOC amino acid synthesis and of course the aqueous solid phase peptide synthesis. But it's, of course, there's a lot of room for work and research.
I see. Okay. So of course we want to leave over some development work also to our customers.
Definitely.
Okay. So let's see, what did we ask Benna? How well can you avoid this classical difficult sequences problem, meaning the aggregation of peptide chains during synthesis?
Yeah, I think the problem with, let's say, the difficult sequences is normally a better aggregation during the organic synthesis due to the hydrophobic interactions of the side chain protecting groups. I think this should be less a problem in water because we have multiple amino acids that are used without side chain protecting groups. So they have quite a polar character, which might be a bigger problem to form the better aggregation based on hydrophobic interactions. But yeah, I mean, it needs to be tested for the specific sequences, of course. We haven't observed any problems yet. For example, heptaarginine, for example, is normally one of the candidates, I would say, is preferred for hydrophobic interactions due to the PPI protecting groups. And for example, we had no problems, of course, as we used no side chain protecting groups.
Then again, one question in the direction of aspartate formation. So the very critical sequence aspartate glycine is then often avoided by using FMOC asp OTBU DMB glycine dipeptide building block. Have you also tried such a dipeptide building block in SMOC?
No, we haven't tested it yet. Yeah, to be honest, in most cases, it's aspartate formation is relevant for either quite long sequences or for sequences that are difficult to synthesize, where you need longer deprotecting times. I mean, an incubation of 3 hours or 16 hours is quite uncommon for most of the peptides. But yeah, of course, in shorter sequences, we haven't observed it in a, let's say, in amount that's critical. As you have seen in the data we've shown, the synthesis of the scorpion toxin, for example, in the target peptide we synthesized directly, there was no visible aspartate formation. It required quite long incubation times to be a problem. But of course, this is related to the sequence itself. There might be sequences where it's a direct problem. But we haven't tested peptide building blocks for reduction of aspartate formation.
Okay, so then one question again to the resins. Have you ever tried the spheritides resin for your technology?
I think we have tried it. We tested a lot of different resins. Yeah, we did try it, but I think the yield was not that good. But of course, we didn't optimize it for the reaction conditions for this specific type of resin.
Okay. Then a practical question to the stability. What about the storage stability? Are your SMOC amino acids also stable in room temperature, fridge or freezer as the FMOC amino acids, or is there a major difference?
So basically, they should be stable even on the table for at least 1 month at room temperature. In the fridge, of course, they are more stable. In the freezer, we never observed any problems, even after 3 years. The stability was not affected. And we even made some experiments with SMOC protected amino acids in solution. They were stable for at least 3 weeks under normal conditions we use in a peptide synthesis.
Okay, so questions are repeating a bit, also coming in via LinkedIn. So the longest peptide you have made by now, you already answered this. Another question via LinkedIn, could the SMOC strategy be used for block synthesis?
I'm not sure what that means.
Honestly, I'm also not really sure. Completely block synthesis. I hope it would say something to you.
I mean, if it could be mixed with FMOC synthesis or VOC-based synthesis, then yeah, it would be possible to mix or to start synthesizing with an FMOC synthesis, add amino acids via SMOC. If this is meant, then it is possible. But otherwise, I don't know what is meant by a block synthesis.
Okay, and then one final question. Again, technical question. What will be, in your eyes, the best base to be used during peptide synthesis in water?
So I think the best base is, of course, the most the cheapest one available. So if it's possible, I would suggest using sodium hydroxide or sodium carbonate as base. Both work quite well. Yeah, if there are ester side chain protecting groups, then they are too strong, so it could result in cleavage of the side chain protecting groups of glutamic acid or aspartic acid. Therefore, it makes sense to switch to weaker organic bases. Piperazine works quite well, and yeah, even piperidine would work, but yeah, I think nobody is interested in using it in a water-based synthesis.
Then one other question, even some have come now. Have you used water in SPPS or also in liquid phase peptide synthesis?
Yeah, of course, the experiments we showed here are all performed in, on SPPS. It's also possible to use SMOG protecting groups in a liquid phase peptide synthesis. Yeah, I don't want to go into much detail here, but of course the ion exchange columns allow for interesting options.
Yeah. So one comment that came in, perhaps that was that block synthesis was an autocorrection of box synthesis, but I guess there is no sulfo equivalent to the BOC protecting group, is it?
There's an equivalent, but it's at the moment we haven't found a synthesis that is, let's say, commercially sustainable. So we're still working on it, but it might be an option in the future. At the moment, the synthesis is too expensive to use it for peptide synthesis.
Yeah. So I currently see no more questions. So thank you, Christina and Sasha, once again for sharing your results with us. And as I see no further questions currently in the chat, to all the audience, if you have any further questions, do not hesitate to send them to us via email or call us, and we will forward the questions also to Sasha and Christina. With this, we would like to close our online workshop now. I just would like to share one last slide. In the meantime, as I already said, Iris Biotech has added the SMOG derivatized canonical amino acids to its catalog portfolio. You can find them on our webshop under Products, Amino Acids, and there the chapter, the 20 SMOG standard amino acids. At present, we provide the canonical amino acids only, but with the time, for sure, several other amino acids will also add to this chapter. Soon, we will provide the recordings of this workshop. As a thank you, you will get with the follow-up email a voucher for a 10% discount on our portfolio of SMOG amino acids, which is valid for the next 2 weeks. Thanks again for joining us. Thanks to all our speakers, and also a big thank you to our QA manager, Klaus Helm, for taking care of the technical support. We hope you could collect some helpful ideas and information from this workshop, and you make some interesting experiences with this new sustainable technology. We are looking forward to meeting you in the next workshop in December with Professor Knut Jensen from Copenhagen. We will announce this December workshop on time on our homepage and via social media. So enjoy the fall 2022, stay healthy, and hopefully see you soon. Goodbye.
Bye.
Bye.
Bye.